Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation I will give you an introduction to how our oxygen microelectrodes are designed and working, which will hopefully familiarize you with them and help you applying them correctly. This lecture will cover the following topics. How do they work? I will then turn to the specifications of the sensors, a long list of them. And at last, I will turn to troubleshooting of malfunctioning microelectrodes. Here you see a photo of an oxygen electrode, both photo of it and one in action. Quenching refers to a process which decreases the fluorescence intensity of a given substance, for example dye. Oxygen have such an ability, and this has for several years been utilized to optically detect oxygen. This slide illustrates how oxygen suppresses fluorescence from an excited dye, which is excited with 620 nanometer light emitted from an LED. Without oxygen, the dye emits 760 nanometer light when the dye molecule jumps back to the non-excited state. In presence of oxygen, the fluorescence is suppressed due to non-radiative energy transfer of the energy between dye and oxygen. Thus, the more oxygen, the less fluorescence. If such a suitable dye complex is dissolved in a polymer matrix and applied on a tip of a tapered glass fiber, you have an oxygen-sensitive optode. Oxygen must be dissolvable in the polymer so it can diffuse into the dye from the sample. We use polystyrene as the matrix, using proprietary method for activating the glass fiber to get optimal bonding of the matrix to the surface of the glass fiber tip. The oxygen concentration dissolved in the polystyrene matrix governs the fluorescence from the dye, and this concentration is a function of the partial pressure outside the polystyrene, not the concentration. The implication that optodes respond to partial pressure and not the concentration at the fiber tip is discussed in detail in the web lecture about amperemetric microsensors. Our amperemetric microsensors, including the oxygen microsensor, do also respond to partial pressure. This is a photo of the glass fiber equipped with a dye containing polystyrene matrix. The fiber is tapered using an etching technique. The fiber is connected to an optode meter, which illuminates the dye by an LED. The light excites the dye, which emits light back with a longer wavelength. With use of mirrors, filters and photodiodes, the intensity of the fluorescence is detected, which is reversely correlated with the oxygen partial pressure at the fiber tip. This can be written mathematically by this Stern-Volmer equation. A Stern-Volmer constant must be found for the specific dye used, and when this is determined, the optode can be 2-point calibrated. Typically, for convenience, the atmospheric and zero oxygen partial pressure is used. The fluorescence intensity is, however, a function of the amount of the excitable dye, and when illuminating the dye, a bleaching process starts, and thus the intensity measured for a given oxygen partial pressure decreases over time as a function of the bleaching. Therefore, it is utilized that the lifetime of the back-emitted fluorescence after an illumination pulse also is oxygen dependent, the so-called fluorescence lifetime. This is illustrated here. The intensity increases during the light diode emission period, and when the emission stops, the intensity decreases, but it decreases faster with oxygen in the polystyrene/dye matrix than without oxygen. This so-called tau response is only to a minor extent affected by the amount of dye, and therefore a much better parameter to utilize than the intensity. The intensity still has a role to play. The more intense the back-emitted fluorescence light is, the more precise the tau response can be measured. So although bleaching does not affect the actual tau response, the calculation of it gets statistically inaccurate with a decreasing intensity, and the resolution of measurements will therefore gradually decrease with the bleaching. The optote meter emits modulated light with the 4 kHz frequency with a 10 milliseconds pulse duration. The optote meter receives therefore a modulated light response from the fluorescing dye with the same frequency, but now with an oxygen-dependent delay, the so-called phase shift. The phase shift is used as the uncalibrated values seen in the Unison software named as delta 5 with the unit degree. This is a mathematical expression of this phase shift. Top to top on a sinus curve is 360 degrees, like in a circle. The less oxygen, the larger delta phi. Typically at 0 oxygen, this value is about 50 degrees, and at atmospheric partial pressure, it is below 20 degrees. It can vary a little, and therefore individual calibrations are necessary. For optodes, which are used with the newest Unison's amplifier portfolio, these phase shifts for atmospheric and 0 partial pressure is determined and stored on the EEPROM, and thus are they factory calibrated. This factory calibration can be retrieved by the user, or alternatively the user can make his or her own calibration. As seen from the Stern-Volmer equation, neither the intensity nor the phase shift is a linear function of the oxygen concentration or partial pressure, and the linearity of the calibrated signal depends on calculations done within the optote meter/software. The relative change expressed in delta 5 decreases with increasing oxygen concentrations, and therefore the signal-to-noise level decreases with increasing oxygen concentration. At 2.5 times atmospheric partial pressure, the signal change is so small with changing oxygen partial pressure that the calculations are not any longer accurate. Therefore, optodes are not suitable for measurements at partial pressures which are above 2.5 times atmospheric oxygen partial pressure. The Stern-Volmer constant is temperature dependent. Thus, the phase shift is also temperature dependent. However, this temperature dependency can be determined and will be the same for all optodes. With this determined temperature coefficient, the optodes can be temperature compensated, provided that the temperature is measured continuously and that the measured temperature reflects the temperature at the optote tip correctly. We recommend, however, to calibrate at a temperature not far away from the measuring temperature. Because the calculations need temperature input, a high signal quality is highly dependent on a high resolution temperature measurement. Low resolution temperature measurements will result in low resolution oxygen measurements. Therefore, Unisons have investigated much time in finding the best possible temperature sensor to support the optote measurements. In case that the setup in which the optodes are used are accurately temperature controlled, the temperature value can be entered into the Unison's logging software and no real-time temperature measurements are needed. Oxygen optodes have been on the market for some years. In 2018, we launched some improvements, including a zero noise temperature compensation, a new ambient light filtering technology, better bleach protection, a more slender design for our 50 micrometer chip optodes, a fast sensor for eddy covariance technique which require response time less than 0.3 seconds, and then an EEPROM which make the sensors plug and play with the unique sensor identification and calibration retrieval. I will now turn to the actual performance and specs of the oxygen optodes. Recall that these specs are only guaranteed with use of a Unison's optote meter. The limit of detection is validated to be about 0.2 micromolar dissolved oxygen. This equals approximately the concentration in water in equilibrium with 0.02% oxygen. We sell glass fiber-based optodes with 50 and 430 micrometer chip. The Opto 50 is based on a 230 micrometer glass fiber, which is tapered to obtain 50 micrometer chip using an etching process. In addition, we have developed a cost-efficient optode based on a plastic fiber, the Optode 3000. This is made for sample measurements where volume is large and high spatial resolution is not needed. This robust optode is shown on the photo, and to the right you see a schematic version. The response time is a function of the time for obtaining partial pressure equilibrium between the sample and the polystyrene matrix. Thus, there is a trade-off between response time and lifetime. A thin polystyrene/dye matrix makes the optode fast responding, but as a consequence, the amount of dye is then limited, and therefore it will bleach faster compared to a slower responding optode with a thicker layer of polystyrene/dye matrix. So the response time is different for the different models. We can make them with a response time down to 0.3 seconds, whereas the large up to 3000 have a response time about 15 seconds. At partial pressures more than 2.5 times atmospheric partial pressure, the relative change in fluorescence with oxygen change is so low that it compromises the accuracy. The recommended measuring range is therefore set to 0 to 50% oxygen partial pressure. The spatial resolution is defined by the length of the polystyrene/dye matrix on the glass fiber tip. This length is about the same as the tip diameter. Thus, the spatial resolution equals the tip diameter. An optode does not consume oxygen. Therefore, when measuring in liquid samples, and in contrast to Clark-type oxygen sensors, there's no diffusion boundary layer which can be affected by stirring. Thus, the optodes are insensitive to stirring. This is illustrated here, where stop and start of mixing a water sample does not affect the measurement. The lifetime depends heavily on use and model. The lifetime for non-physically damaged optodes is a function of how much dye the oxygen tip carry and the tip bleaching rates. Bleaching itself is a function of the number of measurements taken, because the dye must be illuminated every time a measurement is taken, and it is the illuminations which cause the bleaching. Therefore, lifetime is given as a guaranteed number of measurements and not the length of a period of measurements. If the optode is used for continuous measurements, the time to reach end of life is linearly dependent on the frequency used during these measurements. In the Unison software that comes with the optode meter, it is possible to set the measuring frequency to balance the need of data resolution in time with lifetime considerations. Bleaching is faster at high temperatures, and therefore the possible number of measurements before the dye is too bleached to get reliable data significantly decrease at high temperature measurements. Therefore, the optode lifetime also depends on the temperature during measurements. You can check the number of guaranteed points on our website for the different models, which is given for room temperatures. Shelf lifetime, if the optode is stored in the dark, is very long, more than 3 years. The optodes are long-term stable and do not require frequent calibration. As the phase shift to a minor extent changes with bleaching, we do, however, recommend to recalibrate the optode for all important measurements. During high-frequency measurements, recalibration should be done more often compared to low-frequency measurements. Oxygen optodes stand up to 600 times atmospheric pressure when connected to our deep-sea optode meter. We cannot, however, guarantee that the calibrations done at 1 bar gives accurate measurements at pressurized conditions. the polystyrene/dye matrix might change properties which have not been validated in detail. I have already explained that the fluorescent dye bleaches fast at high temperatures. Therefore, we do not recommend using the Optoad at temperature higher than 50 degrees Celsius. At high temperatures, we recommend decreasing the frequency of measurements to increase lifetime. I now turn to troubleshooting oxygen micro-optodes which do not exhibit normal performance. Naturally, small glass fiber optodes are fragile, and the tip might break if it hits something hard. A broken sensor will not get any fluorescent signal back from the fiber, and the Optoad meter software will indicate that with a signal too low prompt. The meter will still try to calculate the phase shift, but there is no real data input for the calculation, and the values will therefore be all over the place. A signal too low prompt could be due to a broken tip, but it could also be due to a broken fiber, which will give the same symptoms. The glass fiber does not tolerate sharp bends, so please be careful when handling the glass fiber. It is not possible to repair a broken Optoad. When profiling in grinding matrices like sandy sediments or the like, the dye can be ripped off partly or complete. We recommend using ampermetric Clark type sensors to profile such matrices. If the dye is partly ripped off, the software will show the signal to low indicator, and the noise level on both uncalibrated and calibrated signals will increase due to lack of data quality for the phase shift calculation. The less dye, the more noise. An Optoad which is associated with a signal too low warning might still be sensitive to oxygen, and it is up to the user to judge whether the data quality is sufficiently good to be used. The cost of shipping, reactivation and recoating the fiber is so high that we do not offer repairing Optoads which lack dye. When an Optoad is end of life due to bleaching, the signal too low indicator is turned on in the software. The warning is triggered when the fluorescent intensity of the dye gets under a certain threshold. This does not mean that the Optoad no longer is sensitive to oxygen, but the calculation of the phase shift is statistically inaccurate. Measurements with such an Optoad are more noisy compared to a new Optoad, and the original resolution has been lost. It is, however, again up to the user to judge whether the Optoad could still be used or must be replaced. As mentioned before, the cost for shipping, reactivation and recoating the fiber is so high that we do not offer repairing bleached Optoads. If the Optoad tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The Optoad tip tolerates almost all possible cleaning substances like alcohols, acids, detergents, proteinase solutions, etc. So it is recommended to insert the Optoad in different cleaning substances to see if it solves the problem as the first attempt to remove the fouling. Do not use organic solvents which will dissolve the polystyrene matrix. We do sometimes see that Optoads used in protein-rich samples like blood lose their oxygen sensitivity when dry, but restore the sensitivity again in water or wet samples. This is due to a protein cover which, when dry, prevents oxygen to diffuse into the polystyrene matrix, but in water or humid air the polymer cover swells and become again oxygen permeable. If chemical cleaning does not remove the fouling and restore normal performance of the Optoad, a physical cleaning is the only solution. For up to 430 and up to 3000 Optoads, it is safe to wipe the tip with a piece of soft wetted fabric or paper. If you hold the Optoad so the tip points away from you, the wipe direction must always be in the direction that the tip points, never against the tip, which will impose a risk of tip breakage. For up to 50 Optoads, physical wiping might impose a risk to the tip. For physical cleaning of such fragile optodes, we recommend that you hook the optode up into a microprofiling system and gently insert the optode into a soft matrix which gives some shear force on the fouling material and remove it. The best material we know of to do this is Oasis flower foam. It should be wetted before inserting the optode. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.